Hi friends, welcome to the channel Learning R is Fun. In our last videos, we have covered regression. Basically, we started with linear regression, then multiple linear regression, and finally we did logistic regression. In this video, we will cover time series data. In time series data, we have data points spread across the timeline at uniform intervals. For today's session, I will take three examples. Basically, these are from book titled A Little Book of R for Time Series by Avril Coghlan. I have given the link in the description for the study of this topic. The first example is the age of successive 42 kings of England at the time of their death. The second example is a monthly birth rate of babies at New York during 1948 to 1960. The third example is about the sales in a souvenir shop at a beach resort in Queensland, Australia from January 87 to December 93. Time series analysis is a vast and complex subject. This analysis is one of the important techniques of forecasting, which by itself is another topic. I think some minimum information is required before we get into RStudio to study, to do some coding in time series. Let's understand certain important terms. A time series may be such that some observations which are occurring at some point of time may get repeated again. So if you take these two repetitions, they will find some correlations between them. This correlation is known as autocorrelation. If these repetitions are at regular intervals, then we can say we have a seasonality. If the mean and variance of the time series remain same along the time, then we have got a stationarity. In the charts, we see three situations of time series where mean and variance remains constant in the beginning. In one case, you see mean is varying. The other case, variance is varying differently over time. The level of the time series is the average. When you look at a time series chart, you may see a trend. Variations which may be either cyclical in nature, seasonal, or random in nature. We can break down these components from the chart. The data can be split into different components, that is seasonal component, cyclical component, like that. If the variance in the graph is constant throughout the timeline from central line, then it will be known as additive. Otherwise, it is known as multiplicative. To decompose a multiplicative time series, we may have to take a transformation of the data using log. We know logarithm of multiplication boils down to addition of logs. R provides modeling the time series, and several models are available. Don't worry, we are not going to discuss them all. Some cursory idea I will give. But please note, the actual implementations of these models through R is very simple. In random walk model, at each step the next step is uncertain, such as in a stock market situation index controlled by huge number of factors. In the AR model, past data helps us to find the regression equation. In the case of moving averages, we predict based on averages of previous points. So, how many points you take to find the average, that is flexible. A basic naive approach to predict a future can be based on last value. But to improve upon that idea, you can do some average of the past data. But better still would be to give more weightage to recent data than older data. And that's what is done in exponential smoothing. I think with this background, we'll go to RStudio. We'll start today's session with a package called TTR. this is to be installed, then we can load it. This package is going to help us in finding simple moving averages. We'll now go ahead and load the King's dataset. The URL I have given, and from internet it has read 42 items. Let's see what is this. So we have got 42 King's ages at the time of their death, and let us get a times series object from this data. So simply you use a TS function, you get a time series object. Like you use list function and data.frame function, like that you use a TS function. Now you got a time series object King TS. This King's TS, let us see what is it. A time series object is being displayed. It initially shows that it is a time series, and then you see there is a start number and end number. These are the number of data points available, and the frequency in which this is displayed is also given. And you have got certain functions like start, end, summary, etc. for a time series. You can execute them and see what it displays. Basically it gives the frequency and the starting element and ending element, and the summary also gives you minimum, maximum, etc., median, mean, etc. Okay, now let's plot a time series. Plot.ts is the function, and you have to give the time series object within brackets. So we have made a plot now, and now let us look at the plot. Here time is in the x-axis, and the data points which are there in the time series object, they are on the y-axis, and you see the ages are between say somewhat very close, maybe. So at the age of 13 itself this king died. Then we have got a king who lived beyond 81, 86, yeah, this is the maximum age. And we see maximum is 86, minimum is 13. Okay, now we can add a regression line to it simply using AB line function. You have to say the argument name is a regression, so reg equal to, then you have to give the regression equation. Regression, we know that regression function lm takes y as a function of x. In this case y is your King's TS and function is based on the x, which is the time. So we draw the line and it shows a trend. Okay, now let us see whether this time series is stationary. If it is stationary, the variances across the spectrum you should have same. Are you able to see this? Here the variances are smaller, whereas the variance is very high here, and this here also, and again it has become smaller. So it's not same. Maybe we will get a information that this is not stationary. How do you do that? You use a T-series package for that. Load that package, and then you use a Dickey-Fuller test, augmented Dickey-Fuller test, which is simply known as ADF.test. And this test will tell us whether this particular time series is stationary or not. So you get a p-value here 0.529. If the p-value is less than 0.05, then TS is stationary. But we are seeing the value is very high, and naturally this time series is not stationary. When it is not stationary, you may not be able to apply all regression techniques, so you may have to change it to stationary. Now we will move on. We will ask what is simple moving averages. R is going to explain what is SMA in the help pane, and we can see like SMA you have got so many other things, EMA, DEMA, WMA, EVWMA, etc. These are all various methods. You can see here SMA calculates arithmetic mean of series, EMA calculates exponentially weighted mean, WMA is similar to EMA but with linear weighting. So many methods are there. Now we will use only simple moving averages and we will create an object King's TS time series underscore SMA 3. What is this 3? Here when you are doing the averages, you have to say how many points it has to average. So I will give initially 3 and let us see how it pans out. So let's draw the plot now. So the previous plot was having more variations. The same thing after averaging you are able to see in a nicer fashion. You get the trend clearly now. When you increase the number of points to be average, it will become even smoother. See, now you got it like this. It's very clear now. During these years, during these numbers, basically, the king, 8th king onwards, up to some 21st king or so, they were living lesser and lesser life. Afterwards, things have started improving. Maybe during this period, lot of intrigue and so much of confusion in the kingdoms were there. So kings were not living. Maybe there were so many wars. You have to read English history for that. So now we'll move on. We'll take another example, that is NY births, New York City births. Let's read the data. It is 168 items. Let us create a time series object out of it. Frequency is 12 with the monthly data and starting period we are giving within concatenation 1946 and first, that is January. So now let us plot this. Here, since 1946 to 1960, the birth rate has been steadily increasing. You can see here. And the variations are also more or less same, but there is slight increase here, it appears. What we'll do, we'll use an aggregate function and we'll use mean for the function to aggregate. So now we have got a yearly averages basically of 14 years, then 14 averages are available. Now this will plot. So now when we are plotting, you are able to see the average birth rate has fallen down initially, and during this period, that is post Second World War, there is a problem of births. After that it started increasing steadily. Before again tapering somewhere around mid-50s. Okay, we'll use a simple moving average also and then again plot it the same thing with averaging for 24 months. So this plot is even smoother. We'll see another concept now, that is decomposing of a time series. Let's see what is decompose. R will tell us decomposition by moving averages. So decompose a time series into seasonal, trend, irregular components using moving averages. Deals with additive or multiplicative seasonal component. Okay, so we are not sure this is additive or multiplicative, but we can apply both and see. First, we will create these components using the decompose function. So you use a decompose function and you give the time series object, and whatever is resulting, that is your components. So I have named it NYBTS components. When you are plotting these components, each component is separately shown. Like trend component is shown like this, and then seasonal is like this, and random fluctuations are also shown. These are individual components are shown, and all collectively put together it is like this. This is what has been observed. Okay, now we will decompose using multiplicative aspect. Assuming that this time series is multiplicative, we will do that. Now again we will plot it. So this plot and that plot, there is a slight change. You can see here these two have changed. The remaining things are the same. The trend is same, so therefore this is not affected. Observed is also same, so it's not getting affected. But you can see the changes in random and seasonal, these are being seen here, depending on whether it is a multiplicative time series or additive time series. Okay, the seasonal component will remove. So for that, what we'll do, from the whole time series, the component seasonal will remove. That is N by BTS components. From that you take a member seasonal, you remove it. Then after seasonality adjustment, what is remaining, that will name it as N by BTS seasonal adjusted. Now this seasonal adjusted is what we will plot next. So we'll execute this and then we'll plot the seasonal adjusted. Now adjusting the seasonality, after that the plot is like this. Okay. So in order to compare, I'm just creating the plots together. So I'll do like this. For MF row, 2 rows and 1. That means 2 plots can be seen on the same screen. And let me first plot the N by BTS as it is, then adjust it. So both are appearing to be almost the same. So the seasonal component is not much in this. You can see these two are same. Okay, we'll move on. We'll go ahead and see the third example, the Souvenir. We'll scan the data and we've got 84 data elements. Here again we'll create a TS object, Souvenir TS, and Souvenir TS, let us see what is it. For monthly data we are getting from 1987 to 1993, January to December. Let's plot this. So I got a plot, and the sales you can see slightly has increased after 91 onwards. After that the sales is not much, and there is a seasonal sales peak towards the end of the year every time. Okay, now but this since the variations are different, this is not additive. So but what we can do, we can create a transformation of the existing time series object Souvenir TS. Will take logarithm and we'll get the log Souvenir TS. Now this will plot. Now this plot is different. You can see after taking the logarithms, the variations which you see from here to here, this is much. Whereas here the variations have been reduced. That's what you can see from here. The time series is a vast subject and we have given only few examples just to introduce the subject to you. And R is having plenty of functions and packages to deal with this time series object, and forecasting itself is a huge topic, and the better the forecast is, the better is for the business or for the community. Thanks for watching and bye from me.